Could an object speeding through our solar system from the void between the stars actually be an alien spacecraft? On July 1, 2025, a mysterious visitor designated 3I Atlas was discovered, sparking a fierce debate. Was it a natural comet or, the first definitive proof of extraterrestrial technology? One prominent Harvard scientist fanned the flames of speculation, while NASA pushed back with hard data. What followed was a clash between radical ideas and rigorous evidence. Let's explore this together. The Atlas discovery in Chile. So, how do we even spot these interstellar travelers in the first place? It starts with a constant, vigilant watch of the night sky. The story of 3I Atlas began on July 1, 2025, at an observatory in Chile. There, a robotic survey system named ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, detected a faint object at an apparent magnitude of 20, making it about 2.5 million times fainter than the faintest star visible to the naked eye. Led by principal investigator John Tonry, the ATLAS system is a NASA-funded project developed by the University of Hawaii, using its twin half-meter telescopes to scan the entire visible sky every 24 hours. When astronomers calculated the object's trajectory, they saw it was following a sharply hyperbolic path with an orbital eccentricity greater than 1, a definitive sign it wasn't gravitationally bound to our sun. Its orbit was an open curve, meaning it came from deep space and was destined to return there. The object was named 3Y Atlas, with the 3I marking it as the third interstellar object ever discovered. It was racing through our system at a stunning hyperbolic excess velocity of 35 kilometers per second, a truly exceptional catch and a prime target for immediate scientific study. Avi Loeb's controversial hypothesis. But what if a new discovery doesn't fit neatly into our existing boxes? This is where science can get heated. Enter Avi Loeb, a Harvard astrophysicist and the head of the Galileo Project, an initiative dedicated to searching for evidence of extraterrestrial technology. Having previously sparked debate by suggesting the first interstellar object, Oumuamua, could be artificial due to its observed non-gravitational acceleration, Loeb turned his attention to 3I Atlas. He pointed to its early lack of a visible tail and what he described as a trajectory that might eventually show subtle deviations not caused by gravity. In a paper released on the RxIV preprint server, a common practice for rapidly disseminating new ideas, he proposed his radical hypothesis. If the object continued to show no outgassing, it might be a technological artifact. He even raised the hypothetical possibility of malign intent, suggesting it could use the sun for a gravitational slingshot to alter its course towards an undisclosed target. Loeb was careful to frame this as an intellectual exercise, admitting a natural comet was the simpler explanation. Still, the mere mention of alien technology from a scientist of his stature was enough to ignite a global media firestorm and put serious pressure on the astronomical community to respond. Media sensation versus scientific method. Here's the thing about alien theories: they travel faster than light speed in the media. Avi Loeb's hypothesis for 3I Atlas was sensational. Headlines around the world, from online blogs to major news networks, quickly latched onto the most dramatic elements of his proposal, the possibility of an alien craft with potentially hostile intentions. This created a fascinating public spectacle, but also highlighted a fundamental tension in how science works. The scientific method is a slow, methodical process that can take months or even years of observation and peer review before any conclusion is reached. In stark contrast, the news cycle operates in mere hours. The global conversation was suddenly centered on a dramatic, unproven idea, while the painstaking work of collecting hard data was just beginning. This put NASA in the position of having to respond not just to a scientific hypothesis, but to a worldwide media event fueled by one of the most compelling questions in human history. It was a classic case of exciting speculation, published on a preprint server before peer review, getting a massive head start on the deliberate, evidence-based investigation. This gap between speculation and verification is where misinformation can thrive. NASA's comprehensive investigation. When a claim is that big, you need the world's premier space agency to weigh in. So, how did NASA approach the mystery of 3I Atlas? They didn't rely on a single instrument. They launched a coordinated, multifaceted observation campaign, allocating dozens of hours of precious observation time on their flagship observatories. This involved the Hubble Space Telescope, using its Wide Field Camera 3 to capture incredibly detailed visible light images, and the James Webb Space Telescope, using its NARSPEC instrument to analyze the object's infrared light for chemical signatures. A network of powerful ground-based observatories, like the Keck Observatory in Hawaii with its massive 10-meter twin telescopes, also joined the effort to track it continuously. This wasn't just about taking pictures. The goal was a deep analysis under the guidance of experts like Dr. Karen Meech, a leading astrobiologist renowned for her work on distant comets. This comprehensive approach was designed to replace speculation with an overwhelming body of evidence. NASA's mission was clear to determine with the highest possible degree of scientific certainty the true nature of this interstellar visitor and let the data tell the real story. Comet behavior confirmed. So what does a comet actually do when it gets close to the Sun? The answer to that question was the key to solving the 3I Atlas mystery. As the object continued its journey inward, NASA's array of telescopes watched its every move. The findings were unambiguous. By late July 2025, as it crossed inside the orbit of Mars, 3Y Atlas started to behave exactly like a comet. It developed a glowing coma, a fuzzy atmosphere of gas and dust, that eventually grew to over 100,000 kilometers in diameter. Soon after, it began to sprout a tail of dust and gas stretching for millions of kilometers, pushed away from the nucleus by the solar wind. Dr. Lori Glaze, director of NASA's Planetary Science Division, summarized the findings clearly, stating that the object was exhibiting all the classic signs of a comet reacting to the Sun's energy. Its initial lack of a tail was simply because it was too far from the Sun for its ices to sublimate. The final verdict from the data was it looks like a comet, and it acts like a comet, so there was no need for an exotic artificial explanation when a natural one fit the observations perfectly. Chemical composition analysis. Here's what really matters. You can learn a lot about something by the light it gives off. Using a technique called spectroscopy, a team of astrochemists led by a figure like Dr. Stephanie Malam from NASA's Goddard Space Flight Center analyzed the chemical makeup of 3I Atlas. This process is like a cosmic fingerprint analysis, where light from the comet's coma is split into a spectrum, revealing the distinct signatures of the molecules within it. The analysis confirmed the presence of water ice, but it was the other volatiles that were truly telling. They found a carbon dioxide to water ratio of 0.6, nearly double the average for comets in our solar system. The data from JWST also revealed significant amounts of carbon monoxide and traces of diatomic carbon, the molecule responsible for giving many comets their distinctive green glow. Far from being evidence of artificial design, these unique chemical traits told a story of its origins. The high CO2 content suggested that 3I Atlas formed in a brutally cold region of its home star system, much farther from its parent star than where our own comets were born. It was a pristine sample from a truly alien yet completely natural environment. Trajectory and safety assessment. With all the talk of alien technology and malign intent, a critical question had to be answered. Was this object a threat to Earth? The bottom line is a definitive no. NASA's Jet Propulsion Laboratory, or JPL, used the global observation data to refine the comet's trajectory with pinpoint accuracy. Their calculations, made public through the Center for Near-Earth Object Studies, showed its closest approach to Earth would be a distant 1.8 astronomical units, which is roughly 170 million miles. There was never any risk of impact. The comet's orbit was also highly inclined at 60 degrees relative to the ecliptic plane, the flat disk where the planets orbit, meaning it was passing high above the main traffic of the solar system. Its perihelion, or closest approach to the Sun, was calculated to be a safe 1.5 AU, well outside of Earth's orbit. NASA's Planetary Defense Coordination Office was therefore able to declare with certainty that this object posed zero threat. This precise tracking dismantled any notion that the comet could be a danger, allowing everyone to focus on the science. Natural anomalies in cometary physics. But what about the unusual traits that sparked the controversy in the first place? It's important to remember that in astronomy, unusual does not automatically mean unnatural or artificial. Comets, even the ones from our own solar system, are notoriously unpredictable. To provide context, NASA pointed to historical examples like Comet 17P Holmes. In 2007, that comet suddenly brightened by a factor of nearly 1 million in less than 48 hours, shocking astronomers as it briefly became the largest object in the solar system by volume. This was a completely natural outburst, not an artificial maneuver. Cometary physicists like Dr. Michael Kelly from the University of Maryland explained that these events happen when sunlight penetrates a comet's crust and hits a pocket of super volatile ice, like frozen carbon monoxide, causing it to flash, sublimate, and release enormous amounts of gas and dust. These anomalies are not evidence of intelligent control, they are a normal and expected part of cometary physics. The strange initial behavior of 3I Atlas wasn't a sign of technology, it was a sign that it was a dynamic natural object. Scientific value of interstellar visitors. So, if it's not an alien ship, why is 3I Atlas still such a big deal? Because its scientific value is immense. Every interstellar object that passes through our solar system is like a pristine time capsule delivered from another star. These objects carry the unique chemical and physical fingerprints of the planetary nursery where they were born. The high concentration of carbon dioxide in 3Y Atlas tells us it likely formed in an incredibly cold, distant region of its home system. Some studies even suggest it could have originated in the Milky Way's thick disk, a population of older stars, making the comet potentially over 7 billion years old, predating the formation of our own sun and planets. Scientists could test this hypothesis by analyzing its isotopic ratios. For instance, the ratio of carbon-12 to carbon-13, and comparing it to other stellar populations. That makes it more than just a passing rock. It's a preserved fragment from the dawn of another world, providing invaluable data for our models of galactic chemical evolution. Comparing 3 interstellar objects. Let me explain why having more than one of these visitors is so crucial. By comparing them, we can start to build a bigger picture of the galaxy. 3. I-Atlas was the third interstellar object detected, and it's fascinating how different all 3 have been. The first, 1E Oumuamua, was highly anomalous rocky, appearing to have an extreme 10:1 aspect ratio and showing no visible coma, which is what led Avi Loeb to his original theory. The second, 2I Borisov, discovered by amateur astronomer Gennady Borisov, was almost the opposite. It looked and behaved very much like a standard long-period comet from our own Oort cloud, with a chemical composition, specifically a carbon monoxide to water ratio of about 0.3, that was remarkably familiar. 3I Atlas falls somewhere in the middle. It clearly behaves like a comet, but its distinct chemical ratios and light-scattering properties make it stand out as unique. This diversity is exactly what astronomers hope to find. It allows them to test whether the processes that shaped our home system are typical, or if we are an outlier. In the end, Comet 3I Atlas wasn't an alien messenger, but it did bring an incredible message. It wasn't science fiction, but it delivered profound science. It carried the chemical secrets of its birthplace, a star system far from our own, giving us a rare glimpse into the diversity of worlds forming across our galaxy. The real story isn't about a manufactured object, but about the natural wonder of the universe and our growing ability to study it. If you want more deep dives into the biggest discoveries from space, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting for us. Thanks for watching Future Facts. In the vast expanse beyond our solar system, the realm of interstellar space challenges our understanding of the cosmos. From the familiar faces of planets like Earth, Mars, and Jupiter, humans have long dreamed of what lies beyond. The heliopause, the boundary where solar influence ends, marks the start of true interstellar space. Since Voyager 1 crossed this threshold in 2012, revealing complex magnetic and plasma phenomena, astronomers have tracked enigmatic visitors like Oumuamua in 2017 and Borisov in 2019. Now comes the mysterious visitor, 3I/Atlas, promising to deepen our cosmic perspective. Beyond the heliopause, our interstellar visitors. Beyond the heliopause lies a vast territory filled with rarefied plasma, cosmic dust, and magnetic fields shaped by the galaxy. The solar wind's protective bubble ends at roughly 121 astronomical units, where Voyager 1 provided unprecedented data on the transitions between solar and galactic environments. This region, once thought to be sterile, teems with dynamic phenomena including plasma waves, magnetic reconnection events, and cosmic ray interactions that alter our view of cosmic landscapes. Dr. Ed Stone, Voyager's project scientist, noted that crossing into interstellar space revealed an environment far more complex than anticipated. Interstellar visitors like Oumuamua and Borisov offer rare glimpses into this frontier, acting as natural probes from distant star systems to ours. These objects carry information about stellar formation processes, planetary system evolution, and galactic chemical composition that would otherwise remain inaccessible. Their study has revolutionized our understanding of material exchange between star systems, revealing the dynamic nature of our galactic neighborhood. The third visitor, 3I Atlas discovery. 3I/Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System in early 2025, marking a historic moment as humanity's third confirmed interstellar visitor. Astronomers worldwide scrambled to confirm its hyperbolic trajectory, ensuring it was genuinely from beyond our solar system rather than a long-period comet. Its approach from the constellation Lynx at extraordinary velocities immediately marked 3I/Atlas as a unique opportunity for scientific study. Dr. Robert Warwick from the University of Hawaii, who also discovered Oumuamua, led early observations confirming its strange orbital parameters and unusual characteristics. Unlike its predecessors, 3I/Atlas displayed continuous cometary activity and potentially larger size, intriguing scientists worldwide who aim to unlock its secrets before it disappeared forever. Initial spectroscopic observations revealed complex chemical signatures suggesting a composition unlike typical solar system comets. The discovery triggered an international observation campaign involving major telescopes across 6 continents, demonstrating the global cooperation essential for studying these rare cosmic visitors. A hyperbolic journey at 58 km. The Atlas survey system, employing wide-field telescopes in Hawaii and Chile, represents cutting-edge technology designed to detect potentially hazardous near-Earth objects. Its success in capturing 3I/Atlas demonstrates how advanced algorithms optimized for fast-moving objects can identify interstellar visitors among millions of routine asteroid observations. Dr. Larry Deneau, who leads the Atlas project, explained that the system's 4-telescope network scans the entire visible sky multiple times each night, creating a comprehensive catalog of moving objects. The detection of 3I/Atlas required sophisticated orbit determination software capable of distinguishing hyperbolic trajectories from elliptical ones. Atlas's rapid response capabilities provided crucial early warning, enabling astronomers to begin intensive observations months before the object's closest solar approach. The system's real-time processing algorithms automatically flagged 3I/Atlas as anomalous based on its velocity vector and trajectory characteristics. This breakthrough exemplifies how technological evolution enables rapid response and detailed tracking of transient cosmic visitors, expanding humanity's reach into the unknown. From A11PL3Z to C2025N1, the naming journey. The naming journey follows established astronomical protocols. When the object was first detected, it got the provisional designation A11PL3Z, which marks it as an asteroid-like object discovered in the second half of 2025. After astronomers confirmed its cometary activity through spectroscopic analysis, it was reclassified as C/2025N1, which means it's a comet discovered in July of 2025. The International Astronomical Union then assigned the official prefix 3I/, marking it as the third confirmed interstellar object after Oumuamua, 1I/, and Borisov, 2I/. The name Atlas honors the Discovery Survey System, following IAU traditions of crediting the discovering institution. Dr. Gareth Williams, director of the Minor Planet Center, oversaw the naming process, which really balances the need for rapid identification with conventions that reflect astronomical heritage. The provisional to permanent designation pipeline usually takes several months, as astronomers need enough observational data to confirm orbital characteristics. This systematic approach helps prevent misclassification and make sure proper credit is given. The naming process also reflects international cooperation in astronomy, since discoveries made by one team benefit the whole scientific community. Committee guidelines are in place to ensure that names remain scientifically appropriate while honoring significant contributions to astronomical discovery. brightness, rotation, and the 29-hour cycle. 3I/Atlas follows a hyperbolic orbit, traveling at about 58 kilometers per second relative to the Sun, which means it's on a one-way trip that will never return to our solar system. Its path cuts through the ecliptic plane with impressive precision, bringing it within gravitational reach of major planets like Mars, Venus, and Earth. Orbital calculations by Dr. David Farnokia at NASA's Jet Propulsion Laboratory show that this object's path creates several planetary encounters, which will slightly tweak its trajectory through gravitational assists. The perihelion passage on October 30, 2025, is the best time to observe it, as it comes within 1.2 astronomical units from the Sun. Scientists like Dr. Alan Fitzsimmons are looking at how these gravity-influenced changes in trajectory can teach us about interstellar dynamics and how planetary systems interact. The approach geometry actually allows observations from both hemispheres as it moves from the southern to the northern skies. Computer simulations predict that these gravitational encounters will speed up 3I/Atlas by a few kilometers per second, showing how our solar system can act like a gravitational slingshot for interstellar objects. Coma tail and cometary activity. Observational campaigns show that 3I/Atlas measures somewhere between 8 and 15 kilometers in diameter, making it quite a bit larger than Oumuamua, but about the same size as Comet Borisov. Light curve analysis by Dr. Karen Meach at the University of Hawaii suggests a rotation period of around 29 hours, which might mean it's a slow rotator, or maybe even has a complex tumbling motion. The object's brightness variation suggests it's not a perfect sphere, maybe elongated like Oumuamua, but not as extreme. Unlike most comets, 3I/Atlas has a persistent but faint coma, and doesn't develop a pronounced tail, even as it gets closer to the Sun. Spectroscopic studies led by Dr. Bin Yang from the European Southern Observatory have found complex mixtures of water ice, carbon monoxide, and organic compounds in its makeup. Its unusual reflectivity patterns hint at surface materials that are different from typical solar system comets, possibly pointing to its formation in a completely different stellar environment. Thermal modeling shows that 3I/Atlas holds onto internal volatiles that start to sublimate at greater distances than we'd expect, which is what creates its unique cometary activity. Oumuamua versus Borisov versus 3I/Atlas. Comparing these three confirmed interstellar visitors, we see, honestly, just remarkable diversity in the cosmic debris traveling between star systems. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, still remains an enigma with its extreme cigar-like shape, and that unexplained non-gravitational acceleration that, well, defied conventional comet behavior. Comet Borisov, found by amateur astronomer Gennady Borisov in 2019, actually behaved like a typical comet, with visible coma development, active outgassing, and familiar spectroscopic signatures. Now 3I/Atlas kind of occupies the middle ground, displaying characteristics that bridge both previous visitors, while also introducing entirely new complexities. Dr. Olivier Haynaut notes that 3I/Atlas shows controlled outgassing patterns and variable brightness that, frankly, just don't match traditional comet models. Statistical analysis by Dr. Alan Harris suggests these three objects represent different formation environments and evolutionary histories. Oumuamua's rocky composition contrasts sharply with Borisov's ice-rich nature and 3I/Atlas's hybrid characteristics. The growing sample indicates that interstellar space contains diverse populations of objects ejected from planetary systems during their formation phases. And Dr. Michelle Bannister emphasizes that only through multiple observations can patterns emerge, revealing the vast variety of interstellar debris shaping galactic material exchange. A 311-billion-year-old traveler. Radiometric dating techniques applied to spectroscopic data suggest that 3I/Atlas could be anywhere from 3 to 11 billion years old, potentially predating our solar system's formation by billions of years. Dr. Dante Loretta from the University of Arizona is leading the research into the object's age determination, using isotopic ratio analysis from remote spectroscopy. Its composition seems to retain primordial chemical markers from ancient star-forming regions, with metallicity signatures that are distinct from materials found in our solar system. The object's surface spectral features indicate the preservation of materials that formed in environments with different stellar winds, radiation fields, and chemical abundances than those that shaped our local planetary system. Computer modeling by Dr. Alessandro Morbidelli suggests that 3I Atlas likely originated from a red dwarf system, where different thermal and gravitational conditions prevailed during planetary formation. This extreme age, paired with the object's unexpected structural integrity after eons of cosmic ray bombardment and micrometeorite impacts, really challenges our current models of how interstellar objects survive such extended journeys. The preservation of volatile compounds over geological timescales raises some intriguing questions about protective mechanisms or internal heating that could maintain structural stability across galactic distances and timescales. October 30th, Perihelion and beyond. The perihelion passage of 3I Atlas on October 30th, 2025, provides the optimal observation window before it begins its eternal journey back to interstellar space. Major facilities including the Vera C. Rubin Observatory, Keck telescopes, Very Large Telescope, and the Hubble Space Telescope will conduct coordinated monitoring campaigns during this critical period. Dr. Lynn Jones from the University of Washington is coordinating the legacy survey of space and time observations that will track the object's brightness evolution and spectral changes as solar heating intensifies. Scientists are anticipating the chance to gather unprecedented data on volatile sublimation patterns, dust production rates, and internal structure through radar observations from Arecibo and Goldstone. The James Webb Space Telescope will attempt infrared spectroscopy to identify organic molecules and isotopic compositions that are invisible to ground-based instruments. Dr. Heidi Hammel, Webb's interdisciplinary scientist, expects these observations to provide definitive answers about 3I Atlas's formation environment and evolutionary history. Following perihelion, the object will fade rapidly as it recedes, making these next few months humanity's only chance to unlock its secrets. The Future Hunt. From beyond the heliopause, 3I Atlas joins Oumuamua and Borisov as rare interstellar messengers that expand our understanding of galactic material exchange. Each visitor challenges existing scientific models, while also driving technological innovations in detection systems, rapid response observations, and international collaboration protocols. The Vera C. Rubin Observatory, which is set to begin full operations in 2025, promises to detect dozens of similar objects every year, transforming interstellar visitor studies from rare events into routine observations. Dr. Mario Jurek from the University of Washington predicts that within a decade, astronomers will catalog hundreds of interstellar objects, enabling statistical studies of their population characteristics and origin distributions. These cosmic messengers carry information about stellar formation processes, planetary system architecture, and galactic chemical evolution happening all across the Milky Way. Advanced survey telescopes like NEO Surveyor and LSST will totally revolutionize our ability to detect and track these visitors, providing early warning for detailed study campaigns. The growing census of interstellar objects will help answer fundamental questions about the universality of planetary formation, material ejection mechanisms, and the prevalence of organic compounds in other stellar systems, potentially reshaping our understanding of life's cosmic context. The journey of 3I Atlas through our solar system really reveals the dynamic nature of our galactic neighborhood, where ancient travelers carry secrets from distant worlds. Each interstellar visitor expands our cosmic perspective and challenges our understanding of planetary formation across the galaxy. As advanced survey systems prepare to detect many more such objects, we stand on the threshold of a new era of interstellar archaeology. Which aspect of 3I Atlas fascinates you most? Share your thoughts below. If you enjoyed this cosmic journey, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries. A massive visitor from deep space is flying through our solar system. The object, now officially named 3I Atlas, has astronomers worldwide both fascinated and honestly a bit terrified. Officially confirmed as the third known interstellar object, it carries an eerie potential. Is this colossal traveler a natural body, or might it be, an alien ship? Recent NASA data has sent ripples of fear and fascination through the scientific community, questioning everything we know about visitors from the stars. The breaking discovery. The discovery of 3I Atlas marked a historic moment in astronomy, revealing a visitor unlike any seen before. Detected moving at an extraordinary velocity exceeding typical interstellar speeds, It challenged existing models of natural celestial object behavior patterns. NASA's advanced telescopes captured data suggesting anomalous properties, including unnatural acceleration patterns and an unusual trajectory that frankly defies conventional gravitational explanations. Researchers like Dr. Amir Siraj from Harvard University have highlighted these deviations as potential indicators of advanced propulsion systems, setting off widespread debate about the object's true nature among the global scientific community. The stunning size of 3Y Atlas far exceeds earlier interstellar discoveries, measuring approximately 10 to 15 kilometers in diameter, and igniting serious discussions about whether we are observing a spacecraft rather than a natural cosmic wanderer. From initial detection through detailed spectroscopic analysis, the international scientific community continues grappling with extraordinary possibilities ranging from exotic comet composition to genuine extraterrestrial technology. The implications of either conclusion would fundamentally alter humanity's understanding of our place in the cosmos and the nature of interstellar space. The Discovery Story. The remarkable story of 3I Atlas begins with its initial detection by the Asteroid Terrestrial Impact Last Alert System in early 2025, when automated survey algorithms flagged an object moving with unprecedented velocity characteristics. Astronomers quickly realized its trajectory was hyperbolic rather than elliptical, definitively confirming its interstellar origin from beyond our solar system boundaries. Its enormous size, estimated to be several kilometers across, dramatically dwarfed the infamous Oumuamua and 2I Borisov, making it by far the largest confirmed interstellar visitor discovered to date. Dr. Robert Warwick, who previously discovered Oumuamua at the University of Hawaii, coordinated initial observational campaigns revealing mysterious activity patterns indicative of possible artificial influence or control mechanisms. The object's calculated path through our solar system appeared to be deliberately planned, with intriguing timing and orbital alignments that prompted intensive scrutiny from major observatories worldwide. Global astronomical networks mobilized for an unprecedented international data-gathering campaign, dedicating thousands of observation hours to studying every measurable aspect of the object's behavior, composition, and structural characteristics before it passes beyond detection range. A stranger in our midst. As 3I Atlas traverses our solar system, its extraordinary properties consistently challenge natural explanations proposed by conventional astrophysics models. The object exhibits complex outgassing patterns inconsistent with typical cometary activity, suggesting an internal energy source actively controlling its emission characteristics rather than passive solar heating. Advanced spectroscopic data reveals a surface composition featuring unusual metallic elements and compounds not typically found in natural asteroids or comets, sparking intense debate about whether it represents an artificial construct. Astrophysicist Dr. Marco Micheli from the European Space Agency has pointed out the object's highly reflective surface properties and precisely controlled thermal emissions as potential evidence of technological design and manufacturing. Most puzzling is the object's demonstrated ability to withstand intense cosmic radiation and extreme temperature variations without apparent structural disintegration or expected material degradation. These collectively puzzling characteristics make 3I Atlas a prime candidate in humanity's ongoing search for evidence of extraterrestrial spacecraft, fundamentally transforming how scientists approach the study of interstellar objects and their potential origins. The mounting anomalies continue defying conventional astronomical explanations while supporting increasingly exotic hypotheses. The predecessors. 3I Atlas follows in the cosmic wake of two notable predecessors that have, really expanded our understanding of interstellar visitors. Oumuamua, the first confirmed interstellar object sighted in October 2017, and Comet Borisov, observed in August 2019. Each of these brought unique mysteries that, honestly, challenged established astrophysical models. Oumuamua's extremely elongated, cigar-like form and its completely unexplained acceleration away from the sun-puzzled experts around the world, while Borisov displayed more conventional cometary traits including visible outgassing and typical orbital mechanics. NASA researchers, including Dr. Karen Meach from the University of Hawaii's Institute for Astronomy, have emphasized just how important it is to compare these objects systematically to really understand the true diversity of interstellar visitors entering our solar system. Their cumulative comparative studies suggest a broad spectrum of both natural and potentially artificial objects traversing our galactic neighborhood, hinting at a far more complex and dynamic composition of the interstellar environment than scientists previously conceived. The sequential arrival of 3 on Atlas has really intensified international calls for establishing dedicated interstellar monitoring programs, capable of detecting and tracking future visitors with enough advance warning for detailed study. The cosmic journey. Traveling at incredible velocity with a definitively hyperbolic escape trajectory, 3I Atlas's epic journey from the depths of interstellar space really captures the imagination of scientists and space enthusiasts worldwide. The massive object appears to have originated millions, possibly even billions of years ago in a distant stellar system, and then embarked on this extraordinary voyage spanning both familiar and unfamiliar regions of our galaxy. NASA's Jet Propulsion Laboratory continues to support sophisticated computer simulations designed to understand how such enormous objects could, successfully traverse vast interstellar distances while maintaining structural integrity against all kinds of cosmic hazards. Dr. Alessandro Morbidelli's groundbreaking work in astrophysical dynamics specifically highlights the numerous challenges faced by such ancient cosmic voyagers during their extended journeys through space. The object's observed interactions with solar radiation, gravitational fields, and interplanetary magnetic environments provide invaluable scientific data about interstellar medium properties, directly benefiting ongoing research into cosmic evolution and galactic structure. Its successful arrival suggests either extraordinary durability of natural materials or perhaps possible artificial construction designed to withstand the harsh realities of long-duration interstellar travel. A scientific goldmine. The unprecedented arrival of 3I Atlas presents an extraordinary scientific goldmine, offering unique insights into the chemistry, physics, and material properties of objects originating beyond our solar system. NASA's James Webb Space Telescope has played an absolutely pivotal role in detecting previously unknown spectral lines within the object's complex electromagnetic emissions signature. Dr. Stefano Bagnullo leads international collaborative investigations that have successfully revealed unexpected complex organic molecules and exotic metallic compounds never before observed in natural celestial bodies. The accumulated observational data promises to shed revolutionary light on conditions prevalent in the early universe and the fundamental processes governing planetary system evolution throughout cosmic history. Intensive collaboration among international observatories has dramatically intensified, strategically leveraging multi-wavelength observations across the electromagnetic spectrum to capture the most complete scientific picture possible of 3I Atlas's true nature and composition. Scientists worldwide anticipate that these ongoing investigations will yield groundbreaking revelations capable of fundamentally reshaping humanity's understanding of the cosmos, interstellar chemistry, and the potential for artificial objects traveling between stellar systems. The scientific community recognizes this as a once-in-a-generation opportunity for paradigm-shifting discoveries. Unanswered questions. Despite extensive international study utilizing the world's most advanced astronomical instruments, there are still, numerous fundamental questions about 3I/Atlas that continue lingering without satisfactory explanations. Its documented orbital anomalies, mysterious surface composition, and those completely unexplained outgassing patterns consistently defy comprehensive scientific explanation using established astrophysical models. The persistent inability to detect conventional volatile substances typically associated with cometary objects fundamentally challenges existing theoretical frameworks and classification systems. Significant discrepancies between observed brightness variations and thermal emission patterns suggest complex surface interactions or perhaps concealed internal energy sources operating according to unknown principles. Leading astrophysicists like Dr. Sarah Seeger propose increasingly exotic alternative hypotheses, including the controversial possibility of artificial origin and extraterrestrial construction. The object's complete behavioral profile remains frustratingly elusive to researchers, continuously fueling heated ongoing debates within the scientific community, while at the same time, demanding expanded observational campaigns to decode its persistent enigmas. each new measurement seems to raise additional questions rather than providing definitive answers, suggesting that 3I/Atlas may represent phenomena extending far beyond current scientific understanding. The mounting mysteries challenge fundamental assumptions about what constitutes natural cosmic objects. The alien question. The profound alien question has resurfaced with renewed scientific vigor as 3I/Atlas continues exhibiting multiple characteristics that many researchers believe point definitively toward artificial origin rather than natural formation. Professor Avi Loeb, the prominent Harvard University astrophysicist and former chair of the astronomy department, argues compellingly that the object's unprecedented properties remain fundamentally inconsistent with any known natural explanations proposed by conventional astrophysics. He suggests that 3I/Atlas could represent a genuine extraterrestrial probe deliberately sent to monitor or actively interact with our developing solar system civilization. This provocative and controversial assertion has sparked intense discussion within both rigorous scientific circles and broader public spheres, challenging established academic orthodoxies. Critics appropriately caution for maintaining rigorous evidence-based standards over speculative interpretations, but the continuously mounting observational anomalies increasingly pressure researchers to seriously consider dramatically expanded paradigms that accommodate the possibility of cosmic intelligence. The escalating debate highlights humanity's gradually shifting worldview as we potentially stand on the threshold of first contact with evidence of non-human intelligence. The implications of either confirming or definitively refuting the artificial hypothesis would fundamentally transform human civilization. Observing the visitor. Intensive observations from major global telescopes have dramatically intensified as 3I/Atlas approaches its closest point to the Sun, offering unprecedented opportunities for detailed high-resolution imaging and comprehensive spectroscopic analysis. World-class astronomical facilities including the Very Large Telescope in Chile, NASA's Hubble and James Webb Space Telescopes, and extensive international survey networks have coordinated completely unprecedented observation campaigns. Dedicated research teams monitor measurable changes in brightness, trajectory, and emission patterns on a continuous daily basis, seeking any anomalous behaviors or structural modifications. The comprehensive data collection efforts specifically aim to capture transient phenomena including possible energy flares, potential communication signals, or unexpected structural alterations that might reveal the object's true nature. The global scientific community universally anticipates that these intensive coordinated observations could potentially provide definitive answers regarding the object's fundamental nature and ultimate origins, possibly marking a genuinely historic moment in humanity's ongoing search for extraterrestrial life and intelligence. The observational window represents our species' only opportunity to study this extraordinary visitor before it disappears forever into the cosmic void. Dawn of a new era. As humanity stands precariously on the brink of potentially transformative cosmic discoveries, the enigmatic presence of 3I/Atlas fundamentally challenges long-held assumptions about our species' place within the vast universe. The object's increasingly complex behavioral patterns hint at the possible existence of a greater cosmic network and unknown intelligences actively operating throughout our galaxy. Leading scientists now seriously consider the revolutionary possibility that Earth and its inhabitants might have been systematically observed for millennia by advanced civilizations possessing technologies far exceeding human capabilities. This profound paradigm shift compels our species to completely re-evaluate our cosmic role, not as passive observers gazing outward at an empty universe, but as active participants within a dynamic, interconnected, and potentially populated cosmos. The ongoing revelations emerging from detailed study of 3I/Atlas herald what may represent a completely new chapter in both cosmic understanding and human evolutionary development. Whether the object proves to be natural or artificial, its mere presence has already begun transforming how humanity perceives its cosmic significance and future destiny among the stars. The dawn of interstellar awareness has arguably already begun. The unprecedented insights from 3I/Atlas have ignited both excitement and genuine concern within the global scientific community. Whether this massive object represents natural phenomena or artificial technology, its passage through our solar system forces a profound re-evaluation of cosmic possibilities. As intensive investigations continue, humanity waits on the cusp of possible contact and discovery. The universe may be far stranger and more populated than we ever imagined. Which aspect of this mystery fascinates you most? Share your thoughts below. If this cosmic investigation intrigued you, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible revelations. After 46 years of exploration, Voyager 1 has finally broken through the ultimate barrier, the heliosphere, and entered true interstellar space. But, the data streaming back from 15 billion miles away is completely rewriting everything scientists thought they knew about the void between stars. This isn't the empty darkness we expected. The space beyond our solar system's protective bubble is alive with invisible forces, mysterious structures, and phenomena that challenge our understanding of the galaxy itself. Today, we're exploring 10 groundbreaking discoveries that prove interstellar space is nothing like we imagined. The magnetic field mystery. The first shock hit scientists when Voyager 1's magnetometer detected something completely unexpected in 2012. Instead of finding chaotic, randomly oriented magnetic fields, the spacecraft discovered that interstellar space has a surprisingly organized magnetic structure. Dr. Leonard Berlanga, from NASA's Goddard Space Flight Center, was among the first to analyze these readings, revealing that the interstellar magnetic field runs nearly perpendicular to our solar system's magnetic field. This sharp 90-degree misalignment suggests we're encountering the edge of a massive galactic magnetic domain. The implications are staggering. These aren't local phenomena but galaxy-wide structures that could influence star formation, cosmic ray propagation, and even the evolution of planetary systems. The magnetic field strength measured at 0.4 nanotesla is actually stronger than predicted, indicating that interstellar space contains more organized energy than our models suggested. This discovery fundamentally changes how we understand magnetic field interactions on galactic scales. The cosmic ray bombardment. Crossing the heliopause in August 2012, Voyager 1 immediately encountered a radiation environment that defied all expectations. Dr. Edward Stone, the mission's project scientist since 1977, watched in amazement as cosmic ray levels spiked by 300% almost instantly. These high-energy particles, accelerated by distant supernova and black holes, bombard everything in interstellar space at intensities that would be lethal to unprotected astronauts. The cosmic ray subsystem aboard Voyager detected particles with energies exceeding 100 million electron volts, radiation levels so intense they would fry electronic equipment within months. But here's the most surprising part. The cosmic ray patterns aren't random. Voyager's instruments have measured systematic variations that suggest interstellar space has natural radiation corridors and safe zones. These findings prove our sun's heliosphere acts as a far more effective cosmic ray shield than anyone realized, protecting Earth and our entire solar system from this invisible galactic storm. The plasma wave discovery. Silence doesn't exist in interstellar space. Voyager 1's plasma wave subsystem, designed by Dr. Donald Gurnett at the University of Iowa, has been detecting constant low-frequency oscillations since entering the interstellar medium. These aren't random static, they're organized plasma waves that create what scientists now call the interstellar hum. Operating at frequencies between 2 and 3 kilohertz, these waves indicate that interstellar space is filled with electrically charged particles constantly in motion. Dr. Stella Ocker, a Cornell University researcher, recently analyzed 5 years of this data and discovered that these plasma oscillations change frequency as Voyager moves through different regions. The waves intensify near density boundaries and quiet down in more uniform areas, creating an acoustic map of interstellar structure. This discovery proves that interstellar space isn't a void, but an active medium where plasma waves propagate across vast distances, potentially carrying information about distant stellar explosions, magnetic field reconnections, and other galactic events happening light-years away. The local interstellar cloud. Voyager 1 isn't just floating through empty space, it's actually swimming through what astronomers call the local interstellar cloud. Dr. Priscilla Frisch from the University of Chicago has spent decades studying this region, and Voyager's direct measurements have confirmed her theoretical models. This interstellar cloud extends roughly 30 light-years in all directions around our solar system and contains about 0.3 atoms per cubic centimeter, which is incredibly sparse by Earth standards but still significantly denser than the cosmic void beyond. The cloud formed approximately 4 to 5 million years ago when multiple supernova explosions carved out a cavity in the interstellar medium. Voyager's instruments have detected the cloud's temperature at around 6,000 Kelvin and confirmed it's moving relative to our solar system at 26 kilometers per second. As we drift through this cloud over the next 50,000 years, it'll gradually affect Earth's climate by modulating the cosmic ray flux that reaches our planet, potentially influencing cloud formation and atmospheric chemistry in subtle but measurable ways. The heliosphere's true shape. Everything we thought we knew about our solar system's protective bubble was, well, wrong. Voyager 1's journey has revealed that the heliosphere isn't the neat comet-shaped structure you might remember from textbooks. Dr. Merav Ofer from Boston University has been leading research using Voyager data, and her team discovered that our solar system's boundary is far more complex and turbulent than anyone predicted. The heliopause, that's the boundary between the solar wind and interstellar medium, varies dramatically in different directions. While Voyager 1 crossed this boundary at 121 astronomical units from the Sun, Voyager 2 encountered it at 119 AU, but in a completely different region with its own distinct characteristics. NASA's New Horizons spacecraft, still approaching this boundary, is providing even more data points that suggest the heliosphere might have a more irregular, possibly even fragmented structure. This discovery has profound implications for cosmic ray shielding and helps explain why the interstellar medium penetrates more deeply into our solar system than models predicted, creating these complex interaction zones where solar and interstellar forces are constantly battling for dominance. The density fluctuations. Interstellar space actually has weather, and Voyager 1 is our very first weather station beyond the solar system. Since 2013, the spacecraft's plasma wave instrument has detected at least 5 distinct density variations in the interstellar medium, each representing a different climate zone in deep space. Dr. Bill Kurth, from the University of Iowa, analyzed these fluctuations and found that interstellar plasma density can change by factors of 2 to 3 over relatively short distances. The most dramatic shift happened in 2014, when Voyager encountered a density spike that lasted several months, indicating passage through a compressed region possibly created by stellar winds from nearby stars. These variations aren't just random, they actually follow patterns that suggest interstellar space has structure on multiple scales. Some regions are compressed by shock waves from ancient supernovae, while others are rarefied cavities carved out by stellar winds. Voyager's measurements reveal that our local interstellar cloud has internal boundaries and substructures, making interstellar space far more dynamic and organized than the uniform medium astronomers once envisioned. The galactic coordinates. Every measurement Voyager 1 takes is helping scientists build humanity's first three-dimensional map of interstellar space. Dr. Nathan Schwadron from the University of New Hampshire leads the team creating these galactic coordinate systems using Voyager's position as a fixed reference point about 15 billion miles from Earth. The spacecraft's current trajectory takes it toward the constellation Ophiuchus, where it will continue for thousands of years unless it's deflected by gravitational encounters. But Voyager isn't just traveling in a straight line, it's mapping magnetic field orientations, plasma densities, and cosmic ray gradients that, vary by galactic location. These measurements reveal that interstellar space has preferred directions and asymmetrical structures aligned with our galaxy's rotation. The magnetic field Voyager measures points toward the galactic center in some regions and away in others, suggesting complex field line geometries shaped by stellar formation and supernova events over millions of years. This galactic GPS system will eventually guide future interstellar missions, helping them navigate the invisible currents and radiation zones that Voyager is now charting for the first time. The temperature paradox. Interstellar space is simultaneously scorching hot and freezing cold, and Voyager 1 has measured both extremes. The interstellar medium itself reaches temperatures of 50,000 to 100,000 Kelvin, hot enough to vaporize any known material. Yet, Voyager's instruments register near absolute zero temperatures because the particle density is so low that there's virtually no heat transfer. Dr. Gary Zank from the University of Alabama explains this paradox. Individual plasma particles move at tremendous speeds, which means high temperature, but they're so spread out that the spacecraft actually experiences the cold of deep space. Voyager's cosmic ray subsystem has detected temperature variations in different regions of interstellar space, with some areas reaching 200,000 Kelvin, where shock waves from stellar explosions have compressed and heated the plasma. These temperature measurements reveal the energy budget of interstellar space, showing how supernova explosions, stellar winds, and galactic rotation, pump energy into the interstellar medium. Understanding these thermal processes is crucial for predicting how interstellar gas eventually collapses to form new stars and planetary systems. The communication miracle. Keeping Voyager 1 alive and transmitting from interstellar space represents honestly one of NASA's greatest technical achievements. Suzanne Dodd, Voyager project manager at JPL, oversees a mission using 1970s technology to communicate across interstellar distances. The spacecraft transmits with just 23 watts of power, less than a refrigerator light bulb. Yet NASA's Deep Space Network can still detect its whisper-faint signals after they travel for 22 hours at the speed of light. In late 2023, Voyager suffered a critical computer failure when cosmic radiation corrupted its flight data subsystem. Engineers led by Linda Spilker performed digital surgery across 15 billion miles, reprogramming 1970s computer code to bypass damaged memory sectors. The repair took months because every command required a 44-hour round trip for confirmation. By April 2024, they successfully restored communication with all 4 active science instruments. This remarkable resurrection really proves that American engineering from the space race era was built to last, giving us precious additional years of interstellar data from humanity's most distant explorer. The Golden Record's journey. Beyond its scientific mission, Voyager 1 carries humanity's greatest time capsule into eternity. The Golden Record, curated by Carl Sagan and Anne Druyan in 1977, contains sounds, music, and images representing Earth's diversity in 55 languages. Dr. Timothy Ferris, who produced the record, selected Bach, Beethoven, Chuck Berry, and traditional music from around the world. NASA engineers designed the record to survive billions of years in space, with instructions engraved in pure gold showing how to play it and how to locate Earth. The record includes greetings from President Jimmy Carter, UN Secretary General Kurt Waldheim, and children from all around the world. As Voyager travels toward the star Gliese 445, it'll make its closest stellar approach in 40,000 years, passing within 1.6 light-years of this red dwarf. Even after Earth's continents drift beyond recognition and human civilization evolves beyond imagination, the Golden Record will preserve our 1970s snapshot of humanity. Carl Sagan called it a bottle cast into the cosmic ocean, and now that bottle has reached the interstellar sea, carrying our message to whatever intelligence might someday find it drifting among the stars. Voyager 1 has shattered, well, just about every assumption about interstellar space, revealing a cosmic environment that's structured, active, and far more complex than we ever imagined. From magnetic field mysteries to plasma weather systems, this 1970s spacecraft continues revolutionizing our understanding of the galaxy itself. Voyager proves we live in a protected cosmic oasis, shielded from the harsh radiation of deep space. So, which discovery amazed you most? Drop your thoughts below. If you loved exploring these interstellar revelations, hit that like button, share with space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries.